Okay, we are BYU Process Control Kitchen, and this is our presentation. So this is our presentation outline. We're going to be focusing mostly on the hardware design and PID tuning for this particular video. The problem that we chose to solve with the process control was the cooking of dulce de leche, which is a time-intensive process. Dulce de leche is a favorite treat in South America, but it takes about 2 hours to make dulce de leche from scratch, and that's with a lot of interaction from the person. But it's simple enough that the process could actually be automated and done by a machine. So we chose to use an empirical FOPDT model because as we were looking at the physical model for this system, we realized that because heat capacity changes over time, as well as while water evaporates, and we have our heat transfer functions via convection and conduction, there were a lot of factors that made it really difficult for us to accurately create a physical model for the system. So instead of trying to do that, we chose to follow an FOPDT model instead. So the hardware design for the system was actually pretty complicated. We use a lot of different stepper motors and Arduinos and controllers so that we could get the entire process to be automated. In the next slide, we'll see a picture of that system. So this system consisted of a mixing pot and a lot of other hardware components that we'll actually take a look at in a video here.
So here we see our stepper motor, which controls our stove, which we have a 3D printed part that controls the position of the stove. And that's hooked up to our Arduino, our first Arduino, which is also hooked up to our thermocouple, which is in our solution, which measures the temperature of our liquid. And this is all controlled through a PID controller that is written onto the Arduino and is controlled through Python, which is running on the laptop, which outprints the position as well as the set point temperature.
And to stir the pot, we have this motor system that we created using a stepper motor that is hooked up to this Arduino right here, and it is programmed to stir every 30 seconds or so to keep it well mixed so that we get a constant temperature profile.
This is a picture of a variable DC power supply. We needed to use this power supply to keep our motors from overheating. We found that they were overheating because they were drawing too much current. This allowed us to control that. Here's a picture of the wiring configuration for our Arduinos, our motor driver, and our thermocouple signal amplifier. This is a close-up of the stepper motor controlling the stove top knob. We 3D printed a component that would allow us to couple better with this metal shaft so that we wouldn't slip when the motor shaft turned. Here's a picture of the cooking pot with the mixing apparatus. This orange cable is the thermocouple going down into the milk mixture. Step for creating an FOPDT model is collecting dynamic data. We connected a step test at a medium flame size on the stove, which resulted in the dulce de leche mixture boiling over in the pot before reaching a steady state temperature. We had to conduct a second step test at a lower flame size, and after 50 minutes we found that this lower setting reached steady state at about 63 degrees. Next, we plugged in this dynamic data to a piece of optimization code, which would find the Kp, Tau p, and Theta p for our FOPDT model. Here are the results of our PI controller. Our PI controller was manipulating the position of the stove top knob using the stepper motor, where one step is the equivalent of 1.8 degrees of a full 360-degree revolution. The controlled variable was the temperature of the dulce de leche mixture in our pot. We also implemented an anti-reset wind-up loop to stop our integral term from accumulating when our stove knob was maxed out because it couldn't generate any more flame size, also while it was a minimum so that we didn't extinguish the flame on the stovetop. In conclusion, we successfully created several batches of dulce de leche using an automated system and a PI controller. Given more time, we would have looked into moving our thermocouples outside of the mixer's path to avoid any sort of disturbance in the thermocouple or temperature measuring, and extending our mixer shaft to reach the bottom of the pot. Because after evaporating off some of the water in the milk, we found that our mixture was ineffective. Thank you.